Our next speaker is a remote presentation from Israel, Elchanan Rappaport, who is president at Gaia Logic, based in Israel. And Elchanan is going to talk about formal verification, security checking. So formal verification from a security point of view. Elchanan is the founder of Gaia Logic. He has 35 years of experience in both simulation and formal-based verification. His customers have included IBM, ARM, TI, National, and Microsoft. For the last 15 years, he has focused on high-end formal verification projects and is a common speaker at formal verification conferences and events. So I'm going to hand over to Elchanan.
Good morning. Okay, no need for me to repeat what's on the slide. Mike just did a nice job of summarizing it. The only comment I'll make, first of all, I pronounce my name Elchanan Rappaport of Gaia Logic, but I'm really not particular about the pronunciation, so no harm done. And I'll just make a comment that this lovely lizard that you see here, that is a Gila monster, actually spelled with a G though. It lives in southwestern United States, Arizona, New Mexico. It's about 14 inches long. And since you guys are in the UK, you still remember what inches are. And it is poisonous. It's very cute. And by sheer coincidence, my wife's name happens to be Gila, which is the Hebrew word for joy, which is not to say that my wife's a monster, of course. Moving on to the next. Okay, so formal, I'm presuming that all of you are familiar with the general concepts of formal and how it works. Over and above regular formal, there are a few vendors out there which have tools which are customized for formal security. Jasper, which is now part of Cadence, has their secure path verification application. Mentor, as part of Quest to Formal, has Secure Check. And Tortuga Logic, which is not a formal company per se, it's more of a security company, has a partnership with OneSpin, and their tool is Prospect. And all of these tools do secure path analysis. How we wish secure architectures look. From a verification point of view, the world would be a much better place if we had all of our secure logic over here in some safe place and a brick wall separating it between all of the rest of our chip, and it would be really easy to make sure that there's no leakage or communication across this boundary. Unfortunately for us, or more challenging, perhaps if you're the type of person who likes challenges, here is a typical secure architecture. This is taken from an ARM website, where you see that there are, within the design, there are many secure areas and many non-secure areas, and they communicate with each other over common buses, common interfaces. And the challenge, and it is a real challenge for verification, and we're presenting a formal approach to this, is to make sure that there's no leakage or violations of sanctity, which I'll explain also, between secure and non-secure regions. Okay, so here is a much reduced version of the previous slide. It hopefully illustrates what's going on. We have some secure data. In this case, it's a memory which contains different keys. A bunch of other non-secure sources. And they come together into common logic. Just to point out my key over here, red is secure, green is non-secure, and blue are blocks which have mixed data in them. There's the combined or alternating packets are sent through a FIFO, which could just as well be a communication channel. It doesn't really matter. The point is that there's the same channel which is being used for both secure and non-secure data. So you can't just key off the signal names. There's a temporal component also. And they come out to a router, which goes ahead and separates the paths. Secure data coming out over here. Unsecured, I'm not sure if you can see my mouse or not. Non-secure data coming off to the green areas. I'll also point out that there is a safe exit here, meaning that even though the signal labeled key match, safe exit, actually does have leakage, if you will, from the secure data, we're not concerned by it because we presume either enough processing has happened or the filtering is sufficient that we're not really concerned about it leaking there. And this is important because the formal tools have to be able to deal with this concept that even though there are by the absolute definition there's leakage to that point, the tool has to be able to ignore it in its further processing. I'll also make the point that when you say security to a lot of people, they think of cryptography, algorithms, and what we're talking about here is not a way of measuring how strong our cryptography algorithms are. That's a whole different area. We're talking at the more basic level of can secure data keys leak from one region to another. Okay, so how would we test this? I mean, how would we quantify the problem we have? We have a handful of secure signals, and in general design, even a large design, it's not going to be a million sources. It's going to be a small handful of secure keys or other information that we want to protect. We'd like to identify all the places it could possibly reach, which is all the outputs of the block or all the top-level signals of the block, which is typically hundreds or thousands. There are actually many destinations in the typical design. And we want to make sure that the data can only reach the places it's supposed to and not reach the places where the bad guys can steal it. It's the skull and crossbones, which I found. Okay, now there's no way for simulation to address this. And even if you've got your regular formal tool set, writing SVA system, Verilog assertions, there's not any way to test this. Okay, just in case it got lost in the noise, I actually had to behave myself to tone down the font on this slide because I had wanted to make it a lot bigger. There is no way for simulation to address this, meaning that, let's say you've got an arbiter. While I, and perhaps most of you in the audience, would agree that the best way to test an arbiter is to do formal. If you've got a reasonable constrained random environment, you could probably get pretty good testing on the arbiter. For this case of data leakage, of secure checking, there is absolutely nothing simulation can do, can even approach addressing this. So we're providing a solution here. I'm not providing anything. I am presenting a solution methodology which is provided by a number of vendors which does address this very directly. Okay, so what have they done? They've created a special command, and each vendor has their own syntax for it, but they're all pretty similar, which says, can you get from point A to point B? So what you do is you have a loop, in this case it's just a tickle loop, from the key memory to, and then all of the possible destinations. And again, you ignore the safe exit, which I made reference to, because we don't care about those. It's one source to many destinations, and something I should mention here also is that the tools are all sensitive enough to identify timing dependencies. What I mean by that is, so let's say you've got a key which you can't the leakage is not such that you can actually get out the entire key A, B, C, D to one of the output pins. But depending on what the key is, the timing of when the valid signal comes on and one of the output pins is affected by what the key is. So a good hacker can have a timing attack, and he can look at the outputs of that valid signal under different conditions and infer from that information about the key, which we don't want to happen also. So the tool is sensitive enough to identify that. And obviously this tool is also sensitive enough to identify any permutations, commutations, if that was a word, modifications of the key. If the key affects the output, that's considered a violation. Okay, so here is a sample run. For the purpose of this presentation, I took the screenshots from Mentor's secure check tool. Thank you, Mentor, for allowing me to use your wonderful tool and capture screenshots. And you see I superimposed onto the block diagram X's which indicate that there was a leakage, there was data leakage, and in this case we're okay because those are the places we expected data to go to, and green check marks where there is no leakage, which is also what we expected. Okay, the tools also offer a very nice debug aid, diagnostic aid I should say, where it will plot onto a waveform the leakage path. So you can see the signal starting off, in this case, key mem indat, and going out to key prime. So you can trace the leakage through internal signals so that when you sit down with the designer and say, hey, you've got leakage here, and he says, no way, no, I don't, you can show, well, it goes through here and here and here. And, of course, he can use that also as a tool to help him fix it. When this concept was first presented to me, I said, what's really the big deal here? You just do a structural analysis of the fan out of your signals, and you can see where data leaks to. That was a very simplistic approach on my part before I really understood anything that was involved. And as I gave the example of the FIFO, where you have the same signal names, but due to the temporal components, sometimes there's secure data, sometimes there's not secure data. If you attempt to apply structural fan out to any normal design, you're going to get a world of false failures, and you won't really know where you have leakage and where you don't have leakage. So you really need the strength of the formal engines, the logical and temporal analysis, to weed out the real security paths from the false security paths. Now let's say that we didn't want to spring for the extra license and just want to use regular formal writing system Verilog assertions. Would we be able to test leakage? Because we still have the same engines running underneath the cover. Any of what I'm presenting here was not development of new formal engines. It's the same formal engines used to prove functional assertions. It's just a different front end, top level, if you will, how to describe the functionality we want and having the same engines churning away at them. So we would need to write a separate handwritten proof for each destination, saying explicitly, here's what we expect the data to be, which proves that nothing else that isn't supposed to be there is there. We need to manually be sure that our functional specification at each point would be correct and that it doesn't allow leakage. And we'd have to do this a few hundred to a few thousand times, which is not really feasible. Okay, now I'm going to move on to a technical point. If you're familiar with formal, you're familiar also with the concept of black boxing, which is where we don't have the real code available, or we do, but its memories or multipliers are not really amenable to formal engines, or we simply want to run faster because with a smaller pruned DUT, we can get better results from our engine. We can get faster, I should say, results from our engine. Now, in property checking, the result of a black box is that all of the outputs of the black box are unconstrained, which means we might end up with false failures, but we know how to deal with them. The important part is that we didn't introduce any escapes, which we don't. But in secure path analysis, it's almost the opposite is true, because if you break a path with a black box, you could be hiding a real leakage path that could be lurking there. So we need to address it. So there are three alternatives I'm presenting. The first is an anti-black box, which some of the tools have nice methods for doing this, or worse, you could write your own, which is a way of providing full connectivity from black box inputs to outputs. And again, here, this might give you false failures, but that's okay. It won't introduce escapes. You could fall back as option 2 and just use the real code and run with that, not black box it, if that option is available. Or 3, and here's my method of preference. It's a iterative, a two-step process where I first, for my loop, where I identify leakage paths from my secure resource to all of the top-level outputs, say. I also have another loop which identifies leakage paths to all of the black box inputs in my design. If I have no leakage to the black box inputs, I don't need to worry about the black box, because if anything can't get in, then it can't propagate out. For those cases where I do find leakage to the black box inputs, then I've got to revert and figure out what do I want to do. Do I want to abstract? But in terms of running the tool, I find I get much quicker results by using this approach of checking my black box inputs and then iteratively adding what I need to add, but I get answers faster. Fault coverage. And this could relate to safety, in our case relating to security. If I have a device that I've tested, and functionally there's no leakage to it. Say my cell phone, which has my credit card numbers somewhere, and the cell phone dies. Okay, I'll buy a new cell phone, probably one with a bigger screen. I'll spoil myself with other features. But the important part to me is that as it's dying, it doesn't start spitting out my credit card numbers to whoever happens to be standing nearby or who have gotten hold of the phone. So the way that we would check this is after checking that we don't have any leakage of our secure data, we can have a nested loop. We can take our list of faults, which is stuck at 1, stuck at 0, or really any other fault we choose to model, and iteratively for each fault, rerun the list of leakage targets and come away with what we have to be concerned about. Now, in the case of this design, I actually did that. I just threw in stuck 1, stuck 0, false to design. I had no idea what to expect. And the result I got was quite useful, and I really wasn't expecting it. I found that if there are faults in the data signals, it doesn't really matter. The design might not work, but I don't have a security concern. If there are faults in the routing fields going into or out of the packet encoder, the data could get routed to the wrong location, which would be a security breach. So going back, putting on my designer hat, I said, okay, let me add a parity bit to all of the routing fields. And if the packet router detects any bad parity on those fields, it'll just drop the packet on the floor and not forward it to anybody. And I reran the formal tool with the nested loop of all the faults and all the destinations, and found that with that fix, I did not have any more leaks, which I thought was a very nice application, that the fault coverage method really actually did work because it gave me real results, which I was able to use, fix my design, and confirm that the fix worked. Let me introduce another concept of data sanctity. Wow, and I see I'm running longer than I thought, so I will speak more quickly, or maybe skip a few things. Okay. In the same way that you want to protect the door, that a way to get through a door that's not supposed to be gotten through would be to steal the key and use the key to open the lock. Another method would be to change the cylinder to one that you already have the key to, and then just open it. So in addition to worrying about data leakage, designs often have secure areas, such as in this slide, the cached key, where the arrows are pointing to, where we want to make sure that the only key that can actually end up there is something that came from the key memory and not from any other source. And this is sort of an analog, I'm not sure the right word, converse, to the case of leakage, because we've got many destinations and only a handful of sources. Okay, so you would write a similar property where the loop would be from many inputs to that single destination. And we said that this is sensitive enough to timing, which is sort of a double-edged sword, because in this case, usually you don't care about the timing that much. You just care that the data can't be replaced. And due to the nature of how logic is written, in the packet encoder, you may have an arbiter where the timing can be affected by requests from non-secure channels, which is really okay, but the tool will flag it as an error. So here's a case where I'm using the Sanctity, the secure path analysis, and getting that result. In this case, I might be able to get away using SVA. Specifically, because it's only a handful of destination properties, I write the property that says, to my cached key, the only input can be what came from key memory. And I will also do a little bit of data coloring, and which I'll explain in the next slide. And this would not be sensitive to a timing dependency, but that could be okay. So here, this is just SVA coding. Assuming that from the key source, the parity of the data of that particular nibble is going to be even parity. Hope I got that right. And from all the other destinations, it would be odd parity. And confirm that what actually makes it to the cached key is only even parity. Okay, so I've talked about secure path analysis versus writing regular system Verilog properties. And in the case of data leakage, I'm almost completely in domain using my secure path analysis tool. For data sanctity, I may be using either. And for functional, when working with security, there are often properties that are just do not express functional properties. The CPU can never enter the root mode unless it's got certain authorizations. And that you just check with regular SVA properties. So I took a controller here. And I think I might walk a little bit quickly through this because I want to get some of the examples at the end. So I took a general purpose PIT controller where there are open source versions out there and said, I want to design a secure version of it. One where I have secure data in Bank 3, and I want to be able to process that data, but I also want to make sure that none of that data leaks out to the rest of the world. And I also want to be able to switch back between secure mode and non-secure mode. So I defined a bunch of properties of my secure mode that when I'm in secure mode, I can't read data from the other memory banks, and I can only write port B, I can't write port C, and I removed the expansion debug interfaces. So I did this, made the changes to design, and I wrote a property that says I can't get from Bank 3 to any of the outputs of the design of the block. And iteratively, the tool identified one security leak after another. So it gave me a list of changes I needed to make. I needed to make sure that when I did a context switch leaving secure mode, a list of registers I needed to clear. I needed to reduce certain instructions from my instruction set during secure mode to disable them during secure mode. I needed to make sure that I'm not going to go into PIC architecture, but there are different ways of modifying the program counter or the status, some of which involve the side effects of executing instructions, some of which are direct update this value, so we have to disable directly updating this value. This may have been overkill. If I want to spend more time on it, I could perhaps relax some of these changes and go ahead and use my secure tool to confirm nothing was damaged. And the tool gave me, in fact, when I was done, that secure data could leak to port B, which is fine, but it could not leak to the other destinations, which is what I wanted. So now I'm going to talk about some customer bugs that I found. These are all real-world bugs. The first is that there was secure data that was allowed to reach a certain place, and the designers were very careful to make sure it couldn't reach anywhere else. And in that same chip, there was a different group, a different bunch of engineers designing the JTAG diagnostic part. I'd say diagnostic here. And they had a rule that said, or a design practice, it said on any interface, check for CRC errors. If you've got CRC failed, then you send the whole bus out to the diagnostic processor to figure out what's going on. So I just took the Verilog, without really understanding the system, I just took the load of Verilog that I got, wrote the property, said secure data can only get to this one specific destination in pink, and the tool directly spit out this leakage path because the diagnostic processor wasn't secure. And this sort of turned the customer on his head, and as opposed to a minor investment in formal where they were just looking to sleep a little better at night, this turned into a full-blown effort where other bugs were found also. And I consider this a success story. There's another bug which I'm just going to skip because it's a subtle bug. Okay, I got 5 minutes. So this is a recent bug I found, and I love this one because it just shows how devious formal could be. The customer design had two controllers with a shared resource, and as the shared resource was attached to one controller or the other, that controller alone was allowed to send transactions to it. And of course, there's a requirement that no data leak from one controller to the other. And the way they protected themselves, they had a double cleanup mechanism. That after each transaction, the transaction would clean up after itself. And every time there was a context switch, meaning the shared resource shifted from one side to another, there'd be a full flush of the shared resource. And I used SVA for this as opposed to secure path analysis because of timing dependency issues. Okay, so the tool was, again, it was just so devious and I loved it. It found a way to break the double protection. The first thing it did was to overflow there were a bunch of FIFOs which were not protected against overflow, so it right away overflowed those FIFOs so that the per transaction cleanup mechanism got stuck and didn't work. And then after it already did that, it went ahead, the designer, it turns out, had made a mistake. There were a bunch of resets in the system. And as opposed to connecting a hardware reset to the flush mechanism, he connected the reset, which in certain circumstances was overridable. So the formal tool also, after overflowing the FIFOs so the cleanup didn't work, it overrode the reset so that the reset didn't occur and leakage occurred. What have we learned? Okay, we've learned that I can talk quickly when I'm in a hurry, hopefully intelligibly. You guys will tell me later. That secure architectures are not as simple as we'd like. We've demonstrated what formal for data leakage is. I should have put this in red again in bigger font. There's no way for simulation even to address this. It's not just a matter of they can get 80% of the way instead of 100. There's nothing simulation can do for this. We talked about black boxing, which is techniques. We talked about fault coverage. We talked about data sanctity. We talked about secure path analysis versus functional testing with data coloring. I gave the example of the packet channel, secure controller. I gave a few real-world examples of bugs. Formal can be devious. I talked about that too. And I'd be happy to address any questions you've got, either now or later on. You can reach me, Elchanan@kilogic.com. I thank you very much for your time, and I'll give the floor back to whoever gets it now.
Yeah, Shan. Thank you. Hello, can you hear me? Yeah. Do we have any questions from Bristol? Do you want to introduce yourself, Anthony? Somebody.
I'm interested in the black boxing that you were talking about, and I didn't properly follow the explanation you gave for your preferred solution to the black boxing. I wonder if you could just go over that again.
Okay, I apologize for rushing that, as I'm sure I rushed many other things too. Okay, so for secure path analysis, unlike black boxing for functional, where you just unconstrain the outputs of the black box, we actually need to confirm that there aren't any leakage paths going through those black boxes. One way to do that would be overkill, just to completely connect everything, abstract, completely connect all inputs to all outputs of the black box, but your tool has to work harder. I claim that if you just take the effort to check that there's no leakage to the input of the black box, then you don't have to worry about any further path propagation through the black box because nothing even reaches the input. And I found that a runtime efficient method of dealing with black boxes, which in most cases will work and won't even require a second round of iteration. Did that help, or did I just repeat what I said the first time?
He's nodding. And yeah, you were intelligible as well during your fast talking, so thanks for that, Elchanan.
Well, thank you.
I think I would follow up on the black box. I wasn't. The solution doesn't seem terribly comprehensive because you either do it to the inputs or you have to connect all the inputs to the outputs or use a real code. Is that correct, Elchanan?
It is comprehensive because if there are no leakage to the inputs, then you're done. If you do find leakage to the inputs, then you've got to go ahead and iteratively find some way of dealing with that black box and add it. So, typically, let's say you had 20 black boxes in your design. At most, you actually have to really deal with one or two of them. If you can take the vast majority of them and just cross them off the list with an easier formal analysis, then you're ahead of the game, and you haven't lost anything in the comprehensiveness of your proof.
Yeah, I think if you put it that way, I can see it's a very practical way of breaking it down to a smaller number of black boxes that you've got to deal with. Yeah.
And you have not lost anything in the comprehensiveness of your proof. I think that's
yeah. Okay, perfect. Good answer. No more questions? So, well, thank you very much, Elchanan, and thank you for the presentation.